As you can see, the pendulum's position changes through its swing. It's easy to see how the pendulum's position changes, but what about its velocity and acceleration? The derivative of position is known as velocity. Velocity is a vector that tells how fast an object is moving and in what direction. In our example, position is a function of time. The equation for position is t squared minus 3t plus 2. Finding the derivative of this function is easy, requiring only the power rule. The derivative of position, velocity, is 2t minus 3. Since the graph of position was a parabola, the derivative would have to be a line. With our velocity function, we can answer a lot of questions about the function. In order to find displacement, we take the integral of velocity. For our problem, we were asked to find the displacement during the first 5 seconds, so our limits of integration will be t equals 0 and t equals 5. The total displacement in the first 5 seconds is 10 meters. Average velocity is defined as displacement divided by time. So in our example, the average velocity would be 10 divided by 5 equals 2 meters per second. Finding instantaneous velocity is different from finding average velocity. Instantaneous velocity uses a specific value for t. For our example, we will find the instantaneous velocity of the marble at t equals 4. 2 times 4 minus 3 equals 8 minus 3 equals 5 meters per second. Since we have velocity, we are able to find the acceleration. Acceleration is the derivative of velocity, and it is the second derivative of position. Our velocity function is 2t minus 3, so acceleration would just be 2. Our velocity graph was a line that had a defined non-zero slope, so the graph of acceleration would either be a horizontal or vertical line. In our case, acceleration is a horizontal line at s prime t equals 2.
Alright, let's go.
As time is no longer a variable in the acceleration function, the acceleration will always be equal to 2 meters per second squared. The particle changes direction when the function changes from increasing to decreasing or decreasing to increasing. We can easily see the change from decreasing to increasing on our position graph, but for more complex problems, we will have to look at the sign of the derivative. As we can see on the graph of the derivative, velocity, the values of s change from negative to positive at t equals 1.5 seconds.